of a particle moving in elliptical orbit is constant. So dA by dt, which is the aerial velocity. Area swept in a unit time is basically the aerial velocity, which is constant. Now, if we look at equation number B, equation B, which is here, this one, we have dA over dt, which is equal to 1 over 2 r square d phi by dt, which is equal to constant, because this side is the aerial velocity. Now, also P of phi, which is given here, P of phi, which is equal to mr square d phi by dt. P of phi over m is equal to r square d phi by dt. So putting this value, which I call equation number 4, this is equation number 4, using equation number 4 and equation 3, using equation 4 and equation 3, we have if we put equation 4 and equation 3, we get, I write the direct equation. A is equal to, equation 4 is this one, and we have equation 3 is A is equal to 1 over 2 integral from 0 to 2 pi, and we have r square d phi by dt, and here we have r square d phi by dt, which is equal to 1 over 2 integral of r square and r square d phi by dt into dt. This is equation number 3. So instead of r square d phi by dt, I will put p of phi divided by m. So we have p of phi divided by m into dt. I can write it is, because this is p of phi, yes. So this is 1 over 2 integral from 0 to 2 pi, and we have p of phi over m into dt. But here we eliminate r from this equation and also phi from this equation. Now the limits of integration are now also changes. So the limits of the integration are now become 1 over 2 integral of p of phi divided by m into dt. Now this is the angular momentum, which is constant, and also mass of the electron is also constant. So we have the only variable quantity, which is t, and we know that the time started from 0 to 1 period. If an electron completes one rotation, let's suppose this is point M, and this electron is moving in this elliptical orbit, so here we are taking the time t is equal to 0. So once it completes one rotation, so the time taken to be 1 period. So that's why the time started from 0 to t. So it means that our area, which is equal to p of phi is constant divided by 2m is also constant, so I will keep it outside of the integral. So we have 0 to t dt, and from this we get area, which is equal to p of phi over 2m times t. This is equation number 5. Now we have equation number 1, which is, I think, equation number 1 is EA over this one. Equation 1 is this one, EA over CT. using equation 5 and 1, we have magnetic moment. Equation 1 is this one, E A over CT. So using equation 5 here, we have E over CT times area, which is P of phi over 2m into T. So T cancel with T. We left with mu is equal to E over 2mc into P of phi. This is equation number, let's suppose 6. Now the angular momentum P can also be expressed in terms of orbital angular momentum, quantum number. Like we already did it. P of phi is equal to L time h bar, where L is the orbital angular momentum quantum number. Orbital angular momentum quantum number, and its value are starting from 0, 1, 2 up to n minus 1, where n is the principal quantum number. Then equation 6 becomes mu is equal to EL h bar over 2mc. I can write it in more compact form like this. Mu is equal to LEH over 2mc. I call it equation number 7. Now equation 7 shows that the magnetic moment of the orbital angular momentum, orbital electron, is an integral multiple of EH bar over 2mc. This implies that this magnetic moment mu is an integral multiple of the quantity EH bar over 2mc, because L is an integral multiple. Its value is 0, 1, 2, 3 up to n minus 1. So it means that this quantity, this magnetic moment, is an integral multiple, which is L times this quantity. And this quantity, this EH bar over 2mc, is called Bohr magneton. In the next video, I'll proceed further from this point, okay? Because the length of the video is almost 18 minutes.